question somebody raised yesterday was, I had written for the energy E lambda V1 plus 1 minus lambda V2. This satisfies this concavity property, lambda E V1 plus 1 minus lambda V2. And this was not connected with whatever FO was doing, this was a property of energy, but you can use this. So for example, suppose I take a diatomic molecule. So this will have, let's say, energy Z1 over R atom, and this is Z2 over, let this be vector R minus R. Okay? Then, this is my V1, this is V2, and I form a molecule. And the molecule says that the energy of lambda Z1 over R plus 1 minus lambda Z2 over R minus R is going to be greater than lambda Z2 equals 2 and lambda equals 1/2. Even without calculating, you can see that E of 1/2 1 over R plus this is going to be H2 molecule. Right? If I take Z1 and Z2 equals 1, so this is 1 over R, this is 1 over R1 minus R2. Right? That's the H2 molecule. It's going to be greater than 1/2. This is 2, so this is energy of helium plus 1/2 energy of helium. So H2 energy is always going to be greater than energy of helium. Okay, without calculating, without anything, just from the concavity properties. These are the kind of things that will become easy once you know some properties. Alright? So this is to answer yesterday you were asking this question. But I'll tell you that. Okay, now. Yes. Okay, so this is done. This is one part, right? Okay. Now the other question you are asking is, why it is maximized? So that okay. So let's do that. F rho for a given density is the true wave function corresponding to rho, right? E plus VEE psi rho. Agreed? Okay. I can write this as psi rho E plus VEE plus some arbitrary potential. Some arbitrary one. Some arbitrary. Okay? Psi rho minus integral. This arbitrary potential corresponds to V external R rho R dr. Agreed? This is corresponding to some arbitrary potential, and this is corresponding to this rho. So this psi is not a wave function for this. So this is necessarily going to be greater than the true psi external corresponding to this T plus VEE plus V external psi V external minus integration. Now I'll just call it V, right? Rho. Agreed? And this is nothing but E corresponding to this V minus integration V rho dr. So F corresponding to anything is greater than for any other V minus this. It would be equality if V corresponding to this. Okay? So it has to be maximum. It has to reach towards the maximum. Fine? Does that answer your question? Okay. Anything else? Now let us try to understand. Talking about derivative discontinuity yesterday. That's when we ended. Well, cool. And to understand these things, it's best to go to some kind of non-interactive. So I was talking about E versus N. And what we said is, if I take N minus 1, and N plus 1, you get energy, which is like this, right? And therefore, what we learned, I forgot to chalk it, but it's okay, we'll do this in white. Delta E, delta rho, for N minus some small number delta, right? Minus delta E, delta rho at N plus delta is equal to I minus A. Is that okay? This is what we said yesterday. This is nothing but the chemical potential. So this slope is chemical potential, which is minus I on the side, mu equals minus A here. Alright? Oh, this is plus and minus. Alright? Now let's look at it from the non-interactive point of view. Suppose I have a system. This is where it picks up. There's something wrong. Alright? And I have electrons filled up to this level. So there's epsilon 1, epsilon 2, epsilon 3. Okay? Non-interactive. Then the energy is only P plus V external. There is no VE, non-interacting system. Delta E, delta rho is going to be delta T, delta rho minus plus V external, right? If I remove an electron, delta E, delta rho, this is the N, right? N minus delta is going to be epsilon 2, right? Minus epsilon. And this is going to be delta T, delta rho, and minus delta. And delta T, delta rho at N plus delta is going to be, because now the extra electron cannot come here, energy change will take place here. This is going to be minus epsilon. Removal energy will be how much? Plus or minus? Energy is 2 epsilon 2, and then you remove the minus epsilon, this minus this. Okay? So you can see right away that this functional derivative n plus delta minus delta t delta rho and minus delta is epsilon 3 plus epsilon 2. Right? I may have missed the signs. But nonetheless, what you see in the density functional description, the functional derivative has a discontinuity even in non-interacting sense. It's not a function of it being interacting system. Right? What would be the derivative discontinuity if this was n minus 1 particles? I'm expecting an answer from you. Suppose the last orbital was not filled. Suppose highest occupied molecular orbital is not fully filled. and delta T, delta rho. How much will it be? What is the energy if you remove? How much energy is required if you are removing the electron? Epsilon 2. How much energy is gained when you are adding the electron? Epsilon 2. What will be the difference? 0. Alright, this is very important because in a system where there is no gap, the change in the functional derivative of t is 0. If there is a gap, it's equal to the eigenvalue difference. It should be epsilon 3 minus epsilon 2. Just change the sign. Okay? Alright, any questions on that? Is this point clear? Okay. So functional derivative changes as you go across the figure because the chemical potential changes. Right? Let me agree with that? Okay. What are the repercussions for an interacting system?
Let me just ask. So for let's say non-interacting system which is finite, so we'll have a energy space in a box.
Yes, yes.
So the energy space will go inverse in the system size.
Energy?
Spacing
Yes.
will go inverse in the system size.
Yes.
So if I am trying to describe a metallic system in a non-interacting sense, so in the thermodynamic limit, should I always?
In the thermodynamic limit, if the system is gapless, metal,
Yeah.
delta T, delta rho will be 0.
Always, that's it.
In a semi-conductor, not.
Yeah.
Okay. So even in the case of interacting system, now I know that delta E, delta rho is equal to some change, right? Non-zero. This implies a derivative discontinuity in V and C. Let me explain that. That is very important for understanding behind that problem. Okay, so now let's see. What is happening is, I'll motivate it system by system. If I have, let's say, helium atom, right? Let's take helium ion. So I have one electron. Okay, I start putting in an extra electron. As soon as you have delta E, delta rho, n minus delta, limit delta going to 0 is equal to minus I helium plus. Alright? As you come in from the lower side, nothing can change, you come up to n. On the other hand, as you go to limit delta going to 0, delta E, delta rho, n plus delta, this is 1. 1 plus delta, this is going to be minus A for helium plus, which is nothing but the ionization potential for helium. Is that okay? Affinity for helium plus is ionization potential for helium plus. That's the same thing. So you have a change. Okay? Now,
So how these two terms are same, ionization potential and ionization potential?
if you take helium, you try to remove an electron, you will have the ionization potential of helium. You take helium plus, you try to put in the electron, it will be exactly minus of ion. Right? Okay. Now you see, you have this system, helium plus, in which I have this equation, minus r del square plus v external plus v R3 plus v exchange correlation phi, there's only one phi, one orbit, equals epsilon phi. Now you add minus r del square plus v external plus v R3 plus v xc. I'll write this for square root of rho n, which is phi for one particle. This is going to be minus the ionization potential of helium plus square root of rho n. Is that okay? Because for a singular part of the system, phi is root rho n, rho 1. And this is one particle. For the other system, square root of rho 1 plus delta over 1 plus delta is going to be minus A helium plus or minus I helium, the square root of rho 1 plus delta over 1 plus delta. That's the normalized orbital for 1 plus delta. I can even remove that normalization thing. It's just write it like this. Is that okay? Any questions on that? Now, rho 1 plus delta is nothing but, from yesterday's thing, rho 1, 1 minus delta plus delta rho 2. This is how I was making a stress connection yesterday. Now delta going to 0, this hardly changes. So this fellow does not change. This fellow does not change. This fellow does not change. This is for 1, this is for 1 plus delta. Subtract. This is almost the same as this. But you get Vxc 1 plus delta minus Vxc 1 is equal to I minus I helium plus I helium plus, which is I helium plus minus A helium plus. I'll wait here and wait for questions. All I've shown you is that if there was some potential for helium plus, I've gotten a potential for the other one, which the difference is some constant. What will happen here is we'll see. Suddenly the potential has jumped. When potential jumps, it does not change the density. The eigenvalue changes. And this is known as the derivative discontinuity exchange correlation potential. Notice that by taking the same orbital, I took helium plus because in that case, there is no jump in the exchange correlation, the functional derivative of the kinetic energy. But this thing has changed. Eigenvalue changes. It changes because of the change, the constant change in the exchange correlation potential. Alright? Have I convinced you there is a change? Now you may ask me a question. The question is that if Vxc 1 plus delta minus Vxc delta is equal to a constant, thus Vxc r tending to infinity go to 0. That means, that's why I made it like this. Suppose this is Vxc helium plus, and this is Vxc helium 1 plus delta, helium plus 1 plus delta. Is this constant change constant throughout? Or does it? We also show by other theorems that this goes to 0. How is that possible? Okay, so the answer to that is, and I'll show it to you in a minute. Answer to that is that the change is constant up to a certain point and then slowly goes to 0. If this delta is larger, this region becomes shorter and shorter. This is delta 2 larger than delta 1. And this is delta 0 smaller than delta. Why does that happen? Okay, so far away, nothing should really be happening. It's only in the interior that it changes by a constant. Okay, let us understand that. I leave that there and talk about things up here. So all these things are related. Sig band gap, this band gap, all these things are very, very related. You have here V xc r going to infinity for a finite system goes to the minus 1 over r. Okay, this is proved. Then this is by check paper by one. Then you also have density for any system as r goes to infinity for finite systems going as e raised to minus 2 square root of 2i r. So density decay far away from the system depends on the ionization potential. Okay, this is 1 bar dV holding the sun. Alright, this can be proved rigorously. Okay? So far away, density goes like this. I'll come back to helium again and show you how this comes about. So let's go back to helium. It's a one orbital system, so I'm talking about phi for one particle, which is root rho, phi for 1 plus delta particle, which will be root of rho of 1 plus delta. Alright? Then from this equation, you can write that V external plus V Hartree plus V exchange correlation is equal to half del square root of rho divided by root of rho plus some constant. I just inverted this Schrodinger equation or Kohn-Sham equation. Is that okay? Alright. Let's go to the limit. Let's now plot potential calculated like this. Now, if I take the difference between the two potentials, Okay, let me just do that first. So if I were to take VXC 1 plus delta minus VXC delta will be equal to 1/2 del square root rho 1 plus delta over root 1 plus rho 1 plus delta minus 1/2 del square root rho 1 over root 2. Because everything else is the same. Density is not different. Are you with me on this? Plus, let's write for this constant for delta plus 1 minus constant for delta. Can you see? Okay. Once I've done that, then Hartree, the density is almost the same, not differ. Almost. Delta going to 0.
That's
a very minuscule difference.
That's a linear approximation.
Huh?
That's an approximation.
That's not, yeah, so I can say that if you were to plot, it would be difference could be somewhere here. Right? Because densities are, one is density for one particle, other is density of 1 plus 10 raised to minus 15 particles. Right? Hardly any difference. Big thing is that jump I minus A is finite. Okay? Alright. Now let's calculate this. If I were to take rho 1, this will be equal to e raised to minus 2I medium plus. As R goes to infinity. I mean, in fact, it's exactly this because hydrogenic, but nonetheless, just like this. Okay? And therefore, del square rho 1 over square root of rho 1 will be equal to 1 over R term will go away, second derivative will be twice, 2 Ag plus ionization of Ag plus. You can check that. Del square gives you d2 by dr square. That will give you 2 Ag plus. And 1 over 2 will give you this. And other term is 1 over R d over d by dr. 1 over R term will go to 0 as R goes to infinity.
In place of root of rho 1 plus delta, that is plugging in that.
What?
In place of root over 1 plus delta. Here.
Louder, I can't hear you.
So in place of root over 1 plus delta.
Yes.
Here you are plugging this equation. Right?
No, this is for rho 1. Now, I'm coming to 1 plus delta. In the limit of rho 1 plus delta, okay? In the limit of rho 1 plus delta, R tending to infinity. Let's see how do I define rho 1 plus delta. Rho 1 plus delta is equal to delta 1 minus delta rho 1 plus delta rho 2. Right? That's how we define it. Now, I have already said this would be in the limit of R tending to infinity, which term will survive? We have already said that in the limit of large R, this is how it goes. Ionization potential for helium is less than ionization potential for helium plus. Affinity of any system is smaller than the ionization potential of that system. So, which term will survive? Which one? This is going as exponential minus square root of I helium plus, and this is going as e raised to minus square root of 2 affinity of helium plus. Affinity is always smaller, so in R tending to infinity, only this term survives. And therefore, 1/2 del square root of rho 1 plus delta over square root of rho 1 plus delta is equal to A helium plus. Is that okay? So if I were to plot it, and inside, this is the limit of R tending to infinity. Inside there will be hardly any difference. Or inside, rho 1 is almost same as rho 1 plus delta. But inside this fellow goes to 0. Hardly anything. This only survives because this goes exponentially down. Right? So, inside the potential is the same, whatever. Outside, the potential for helium plus is going up to this. And for helium, it is the same, but it is going up to this. Now let's make it. This constant is I helium plus, this constant is A helium plus. Agreed? I've just written the del square terms. However, I want them to be 0. So I'll shift. I wish I had colored chalk. If I shift this, I shift by only this much. It comes here. If I shift this fellow comes here. And this gap is I minus. So the difference, if both are going to 0, is some constant I minus A, and then far away it goes to 0. And now you can see, smaller the delta, farther out would this fellow go to the constant. And therefore this constant will keep going further and further. This is what happens when you try to replace a non-local theory by local theory.
Can you repeat the last bit?
Okay. Now, you see when you look at this, smaller the delta, suppose delta is 0.2, and this fellow will start dominating faster. He will start dominating somewhere here, right? So he will go to constant somewhere here. If I make it smaller, this will start dominating farther out. So the difference constant will move farther and farther and farther out. And finally the difference goes to 0. This is because we're trying to do a highly non-local theory through a local theory. Somewhere this thing has to come in. So I went through this example, decided to show you exactly why this gap is coming. I'm trying to do a local potential for a highly non-local problem. Okay? And by the way, just on the side, this behavior also proves the ionization potential here, because in a cone-sham system, the density as R tends to infinity will be dominated by e raised to minus 2 square root of 2 epsilon max R. It is only the highest occupied orbital that will go farther and farther and farther out because the value is very small. All others will decay much faster. Right? So this again shows you, giving epsilon max equals minus. So all these things are related. The correct asymptotic limit of the potential, the derivative discontinuity, the ionization potential theorem. All these are connected to the behavior of the density far away, right? How it decays, how it depends on the I and A. Alright? These are all connected. So this is, I am motivated to a non-degenerate system where the orbital remains the same, that there has to be jump. Is that okay? And there is no reason why it should be limited to only 2 electron non-degenerate system. If the exchange correlation potential is jumping, if the exchange correlation potential is jumping, then delta of delta EXC over delta rho is non-zero. I would care for any system. I'm not going to argue. Is that okay? And it will be greater than 0. Because finally it's related to I minus A. I minus A is always greater. Any questions? Because this is a very subtle concept. And in the meantime, I'll have a bite of samosa. Where is the samosa from? Hey, where did it come from? Samosa kahan se aaya? This is more like dosa samosa. The filling is not dosa ka naam jaisa. So on one side is huge samosa. Any question?
So the source of derivative discontinuity is the inadequacy of the DXC due to the locality.
True.
The local approximation.
Yeah. We are trying to do self-energy, which is a non-local operator, replace it by a local operator. Right? Or somewhere it has to show up. A non-locality which comes, somehow you're trying to bring it somewhere.
So basically, we are clinging on to one functional, but as the number of equation changes, the effective charge density background actually changes.
Yes.
But that information is not going back into the VXC.
Yeah, it is going back to that jump.
Yeah, it's going back to that jump.
Yes.
So that's why we have to have that jump.
Another way of thinking about it is that if you have this large system, now I'm trying to bring in an extra electron, but only a small fraction of it. Smaller the fraction, farther away it will be. So it's coming, right? Now, when it's trying to come, so only here the potential goes as minus 1 over r. Here it doesn't change. So all that mixture gives you a constant. It's a very subtle concept. Okay? Now,
So sorry, I mean just
please.
So if again like one can back calculate the jump into the VXC,
Yes.
then will that solve the derivative?
Yeah, but to back calculate, then you have to solve the exact problem.
Yes.
So there's a problem.
There has to be some reference frame to guess the exact.
Yeah. So one can't guess it. You just try to make functions. I think he's made some functions with the proper band gap. Okay, so now, any other question? Well, this is very, very important.
Let's say, one included some kind of retardation, because if it was self-energy, I had some sort of dynamic effect which will.
Yeah, but we're not doing dynamics.
No, that's what I'm saying. So if, is there a way to try to cure the problem?
Now, if suppose you're doing dynamics, then only if the electron is coming in, right? The moment it starts becoming part of the system, there will be a jump. This fellow has to stop it.
No, I was just wondering that beyond this sort of, the functional, of course, here is more like the arbitrary exchange kind of function. Because we have to sort of add the next order correction, let's say.
No, but in an exact theory, I'm doing exact theory.
Yeah, that's what
There is no next order correction. It's exact. Everything is being derived as exact.
Yeah, but then we are assuming that this is exact what the VXC is exact.
Yeah,
VXC
so the jump is in the exact VXC.
yeah,
It's
but
not
the real
in
problem doesn't have,
Hmm?
the real physical problem is.
But I'm not talking about a real system, I'm talking about a virtual system. That just gives you the density. And we are trying to extract as much as possible, and that's asking too much. Right?
So,
You're traveling in a truck and you're saying, give me the comfort of a Mercedes.
So the supplementary actually is that.
Yeah, it's now our omega.
Omega. But now we are having an effective field where we don't want to bring that omega in the picture, because with the wave functions we don't get, there is no handle to get energy back. That's
you also make it omega dependent theory, or it's a different.
Yeah, but this theory is thinking is very different.
Yeah.
So one has to
And
live
it
with it.
has to be a non-interacting regime.
Yeah.
So one has to live with it. You're trying to mimic an interacting system through a non-interacting system, and you want that when I add an extra electron, everything should come out alright, the potential has to jump. It has no sense, right? Okay. This has ramifications for band gap problem. Okay. Now suppose I could do exact calculation in a semiconductor. So we talk about exact on channel. Alright? It will give me a valence band, field, and a conduction band. Up to this, all orbitals have no meaning, and this is conduction band, valence band. This is virtual orbitals. No meaning. Only this has meaning. Right? So this gap ideal would be have no meaning. Ideal. But now let's see, in a semiconductor you would have hope that if I add an extra electron, if I add an extra electron, so hope, add an electron at the bottom of conduction band, nothing would change. I mean, this is like one electron in 10 raised to 20. It's really a minuscule amount. RT would not change, nothing would change, right? So one would go at E, cone-sham conduction band, lowest conduction band, right? So E cone-sham, LUMO, lowest occupied molecular orbital, minus E cone-sham, HOMO. So this is bottom of CV, and this is top of VB, EG. One would hope that. So nothing is changing, right? But now we have to realize that this, as I said earlier, is delta T, delta rho, n plus delta minus delta T, delta rho, n. People usually write n minus delta, but we'll take delta, going to n from delta minus side, it's the same as n. Right? This is this. However, there's a possibility, now because you're changing this, that E LUMO would also have this. And this, he said, in a gap system, where will be. Let me come to this argument from another point of view. From another point of view, it will be that E, as I was asking in the morning, gap fundamental is defined as I minus A, ionization potential. So you take a semiconductor, remove an electron, takes I, given electron, it comes to the bottom of the conduction band. But as you add an electron, the whole thing may jump. So you have this E, CB, LUMO, KS, E, valence band, HOMO, KS. And up to here something is failed, and this is delta E Kohn-Sham, and you add an electron, 1 in 10 raised to 23. This whole thing may jump by this constant. This is gap equals R minus A, which is different from delta EKS by this much amount. Delta. So even if a real system existed, if it is a semiconductor or an insulator, the KS gap will not give you the proper band. So what people do if you want to do a band calculation, they design potentials or functionals that give you good gap. He is one of those he has designed, the others who have designed it, right? So you can fine tune your system to give you okay gap. Somehow it mimics the discontinuity. But then Kohn-Sham theory is to give you the correct density, not the gap. So even if you get a good gap, you may say I'll get a good gap, you're not sure of the density. So I think I'll stop here.